Okay, so in the previous video, I mentioned that the linear regression coefficients are actually related to the covariance or the correlation coefficients, right? With the graph, it was clear. And then mathematically, you can show that the OLS estimator, that minimizes the sum of squared errors, can be written in this way: covariance divided by the variance of x. Or, so remember, covariance, correlation coefficient can be obtained by standardizing the covariance by the standard deviations. So you may rewrite this form using the correlation coefficient this way. So you have to divide by standard deviation y, so compensate that by this and like this. So, and it's intuitive. Basically, linear regression and correlation coefficient and covariance all about the linear relationship. So there must be some clear relationship which is explicitly derived in this by this formula, right? And also, by the way, the intercept is a little bit different. Intercept is more about the parallel shift. So the slope is more like the relationship direction and the strength, but the intercept is like a parallel shift. So it just follows. It adjusts for the mean averages. So average of y minus average of x. So the intercept is to adjust for the averages. And then we know this gives you this. From this you can see that you can calculate the coefficient, the OLS estimators, beta 0 hat and beta 1 hat, based on covariance, variance, or correlation coefficient or standard deviations and averages, right? Then what is unknown? What's the problem in calculating this? From the data example, in our example, cost and output, what you cannot calculate. Okay, so obviously nothing. You know how to calculate the mean, sample mean. It's pretty simple. You know how to calculate the sample variance. You know how to calculate the sample covariance. So what I'm telling you here is calculating the OLS estimators is actually pretty simple. So I explained as if it's pretty complicated minimization problem, right? That is right. Theoretically, that is right. But in the end, what Excel does is simply calculating this. And of course, it's pretty simple to Excel. Excel computer can do it like this. Okay, so from the example data, you can calculate these mean, variance, covariance. Not a problem at all. You know how to do them. And then from there, you can calculate the slope, the intercept. Not a problem at all. So just in case if you wanted to calculate the OLS estimators by yourself, this is how you do it. Or if you want to make your own program for OLS estimator, this is the easiest way to code it. Of course, actually, yeah, coding, you don't need to code it this way, but so this is the easiest way to understand how you calculate this. Okay, now then back to the real data set about returns to education example. So we defined X as the years of education and Y as the hourly wage. And I calculated their basic sample averages and sample variances and their covariance. So from these numbers, so on average education was 13.1 years and variance was 6.3 years. And the average hourly wage was $7.7 and the variance was 33. And covariance was 4.7. In using these numbers, calculate the OLS estimator of the slope, the returns to education, beta 1. What is the estimator for beta 1? remember this is the formula. So just choose the correct numbers. Okay, it's pretty simple. The covariance is 4.7 here, and denominator is the variance of x. Variance of x, 6.36. So that's in the denominator. And then you get 0.742 approximately, up to the rounding error, right? And then given this slope, what is the intercept? Formula is given again here. Calculate the intercept. Of course, you use these numbers. So you need average of education, average of hourly wage. Average of hourly wage is 7.77, and here x bar is 13.1, and multiply the calculated slope. So then you can calculate this. So average hourly wage minus estimated slope times average education. Then you get minus 1.951. So compare the results. So 7.742 minus 1.95. Similar, of course, the difference is the rounding error. Rounding error happens in our example, rounded up to the second place. So I showed you how you calculate. OLS is actually pretty simple to calculate. It's not something very complicated. So Excel does a lot of work, but it's not that much work. Okay? And now the next topic is how to assess, how we would like to evaluate how good we are doing. How good, I would like to quantify how good I'm doing. This regression model is pretty accurate, something like that. So then we can use the residual sum of squares again, or sum of squared errors again. So exactly, so calculate the residuals and square them and sum them. Then this is the amount of residuals still remaining after the regression estimation, right? Then there must be, we may compare the size of the residual should be compared to something comparable things. What that is the regression sum of squares, SSR. So regression sum of squares is this. So this is the predicted outcome, predicted y, and like calculate the deviation of the predicted y from the mean of the observation, and take square and sum. So remember, by the way, you have seen a similar form like this when you calculate the variance. If you divide it by n or n minus 1, you get a kind of variance. So it's simply it's not average, but the summation of predicted values square deviations. So it measures the variation in the predicted value, fitted values. So this explains how much your prediction moves around. So how much you explained the outcome by the regression. So this is, let me show you one more thing. This is another sum of squares. So now you are using the original observation, y. So exactly this is the variation. You can calculate the variance of y from this by dividing it by n minus 1. So this is the total sum of squares, SST. So then we may find them, sum of squares, in here. So remember, this is sum of squares. Sum of squares, this is from the fixed cost, marginal cost example. This is the total sum of squares. Total sum of squares in the observed cost. Observed cost varies this much over 12 months observation. And like the variation, so the cost changes over time because you produce different amounts of productions, right? Products. So you explain, so the change in your production can explain this much. Out of 425 variation, the change in your output can explain 395 something. This is how much you could explain using the variation in the output amount. But still, 29 something is not explained. It's residual. So you can just call this an error. I don't know why you observe this much unexplained part. So it's just an error. So that means then what's interesting here is the total sum of squares. So through over the year, over last year, your cost changed a certain amount, changed 425. That can be perfectly decomposed into explained variation and unexplained variation. Explained variation is explained by the regression model or explained by independent variable x. So you produce different amounts, so this much is explained. But still, I don't know why there are additional randomness, unexplained parts. So this is decomposition. You can decompose the total variation of your cost into two parts, and then you so I showed you these are sum of squares. These three numbers are sum of squares. Now then, you can calculate the proportion of explained parts and proportion of unexplained parts. If you think it's 100%, 100% is the total variation, 425, right? Out of that, you explained a lot, huge amount. So that is called the coefficient of determination. So out of the total sum of squares, how much is your regression sum of squares? You explain this much. Or 1 minus unexplained part, unexplained proportion. Okay? So this is given in here. So if you calculate, let me do it this way. If you take the ratio between these two guys, 395 divided by 425 is this number, right? So the R square is calculated by the ratio of these two. How much you explain out of the total variation, right? So this ratio, if the ratio is close to 1 or 100%, then you are explaining almost everything. But if it's 0, that means you cannot explain anything. So this measures the strength of the relationship, how much you explain or how small your residual is. The larger the R square is, the stronger the relationship is, and the smaller the residual is, right? And as I said, as you can see, we could, in our simple example, 93% is explained. And then that means the other around 7% is not explained. That's 7% is attributed to a random error, unknown error. That's not explainable. And also, there is an interesting relationship. The R square is related to the correlation coefficient because this is about the strength of the relationship. So in particular, we can calculate the correlation coefficient between the actual observations and your predicted values. Of course, if your prediction is perfect, then the correlation coefficient will be 1. And if the correlation coefficient is close to 0, that means your prediction is bad and there will be larger residuals. So, and mathematically we can show that this is actually the square of the correlation coefficient. So that's why we denote it as R square, right? So if R square is 0, that means 100% residuals. There is no linear relationship, right? So that's the implication of the correlation. Or if R square is 1 in the other extreme, That means there is a perfect linear relationship between x and y. So all the data are perfectly lined up. So again, the relationship is strength of the linear relationship is how much you explain by the linear regression. So they are closely related, and in here, this is correlation coefficient between y and fitted values, right? So if you square that, if you multiply this twice, then you will get this again. Same number again, right? That's how you connect the r square to the correlation coefficient. So this is basically correlation coefficient. I don't know, like correlation coefficient. Between correlation coefficient between the actual observations and fitted values. Okay. Yeah, I explained. By the way, there is another thing I could mention here is adjusted R square. Here we consider only one variable. So adjusted R square is not important right now. But the problem is when you have more variables, say like you may utilize not only output but other variables, then you have to adjust the R square based on the number of independent variables, number of x variables. So technically, mathematically, we adjust those measure, but we are not going to study that right now. So like if you take another course, you will learn this adjusted R square. I'm not going to say that here. Okay, so we learned a lot of things. So in the next slide, I'm going to stop right here. In the next slide, I will go back to the real data, education example. So, and I will wrap up the semester, the course. Next one will be the last video for this semester. Okay, thank you for watching and see you in the last one.